So let's look at another example of using the chi-square one-way goodness of fit test. Suppose you're a demographer for the US Census and you want to double-check the validity of the American Community Survey. So suppose you think there might be some errors in your sort of sample, and you're concerned that your sample might have some problems. Well, based on prior studies of the population, you expect the sample to consist of 85% who identify as white, 10% who identify as black, 3% who identify as Asian, and 2% who identify as others. So this is self-identified race or ethnicity. And what you want to do, the idea is that you have these sort of expected or claimed proportions or percentages in the population. You want to use your data to make a sort of chi-square one-way goodness of fit test. Does your data conform to this distribution? So we're going to conduct a two-sided chi-square test. So we have the following hypotheses. The null is that the population proportion for each of our different categories, or each of our different self-identified racial or ethnic groups, those are equal to what we'd expect, right, based on prior research. So we'd expect roughly 85% to be white, 10% to black, and so on and so forth. The alternative is that at least one of these proportions in the population is not equal to its claimed or hypothesized proportion. We're going to set alpha to 0.05, which again will affect our critical value and our calculation of our p-value. We're going to use statistical software to actually conduct this test. You could calculate it by hand, however. When we look at the statistical output, okay, we see that we get a chi-square test statistic, a set of degrees of freedom, and a p-value. The chi-square test statistic is 2.37. If you were to do the calculations by hand, you would obtain the same kind of result. The degrees of freedom is k minus 1, so since k is 4, we have 4 different categories. Our degrees of freedom is 3. That affects the shape of the chi-square distribution, which in turn affects the calculation of our probability value, or p-value, and it affects our decision when making a comparison between the critical value and the chi-square test statistic. Looking at the p-value, we can see that we failed to reject the null at the alpha of 0.05 level. That's because the p-value is 0.50 roughly. What this suggests is that our data are in fact consistent with the null hypothesis. We can look at the p-value from this test visually. So recall that for the chi-square test, the p-value is simply the probability of obtaining a test statistic greater than or equal to the one we observed. Well, the one we observed is 2.37, and you can see that it's right there, almost in the middle of the chi-squared distribution model. That area to the right, if you take the total area under the chi-square distribution model, that area under the entire curve is 1. That area to the right of our chi-square test statistic, reflecting the probability of obtaining more extreme chi-square test statistics, that's 0.5. Right? It's quite likely, right, that we would obtain a more extreme value. Therefore, we fail to reject the null hypothesis at the alpha 0.05 level. It appears, based on our study, that the composition of our sample, it's consistent with that from previous studies, suggesting that we don't have too much to concern ourselves about in terms of knowing whether or not this is a flawed sample. A few things to know for the chi-square one-way goodness of fit test. It's used to evaluate some claim about the distribution in the population of a single categorical variable. We use it when we don't have a population, just like all the other inferential tests we've been talking about. If we had the population, we could just look at it and just compare somebody's claims about that population with the population itself. Since we don't have a population, we want to conduct the chi-square one-way goodness of fit test, in which we use a random sample of data to evaluate somebody's claim. The chi-square test statistic, it's plotted on the chi-square distribution model. That's just a probability distribution, just like the standard normal model, just like the t-distribution model. The chi-square test statistic is just a function of those expected and observed counts. The more extreme values of the chi-square test statistic, that suggests a greater discrepancy, a greater inconsistency between the data and the claim distribution, leading us to, in fact, reject the null hypothesis. With that, we conclude our discussion of the chi-squared one-way goodness of fit test.